talk about binary relations. Just a reminder that this topic is covered in Packet 5, which is on your Moodle course page. Lab 4 is coming up. It's due on Tuesday. It is quite short. It'll probably take you about 30 minutes to do. It is on NovaNet, so please don't wait till Monday night. Go ahead and do it. Like I said, it only takes about 30 minutes. And homework 8 is going to be due the following weekend. We're not going to extend that, so don't wait till the last minute. And then the reason for that is that homework 9 is on counting, and that is probably the most challenging material for the rest of the class. So the next thing after this is going to be hard, so make sure you leave some time for studying on counting. So binary relations is not too hard. We just have to do a lot of definitions. We have a couple of, announcements. One is I extended the deadline for homework 7 to tomorrow. Happy Halloween. And the lab 4, like I said, is due on November 5th. Homework 8 is due on the 10th. That's a Sunday. It's binary. So the login and the password are binary. But that's also on the WebAssign instructions. And if you looked at them earlier and they were bad instructions, look back at them. I fixed them. Okay, so now today we're going to talk about binary relations. And binary is a word that we all know. It means two. And relations is probably a word that, you probably think of some weird stuff. But it's actually a mathematical term for relationships between mathematical objects. And so a binary relation means relationships between pairs of things. So what kinds of things can you think of that represent relationships between two things? What'd you say? A coordinate plane. Good. So the Cartesian coordinate plane is a really good example. So what we're going to talk about in this section is the way that mathematicians have generalized stuff about the coordinate plane. So that was a really good example. So the coordinate plane is the set of all relationships between all pairs of real numbers. So it is a relation because it is a way of relating the real numbers on the x-axis with the real numbers on the y-axis. The fact that it's all of them means it's not a very discriminating relation, but it still is one. And actually, any graph that we can draw on the coordinate plane is what we would call a binary relation. So any graph represents a relationship. And we're used to that. So for example, f of x equals x squared is a relationship between x and y values. And so we say something is on that graph if I have an x value and the y value happens to be the square of that, then that's in that function. And if it's not, it's not. So every pair of numbers on the coordinate plane actually has a 0, 1 value for this function, right? So if it is, one of them is x and its pair is x squared, that is in this binary relation, and if it's not, it's not. Other examples. Division. So divisibility is also often thought of as a relation. So let's give an example. Actually, I already have one of those. So here's a set, for example. So this is a relation, and the set that we're going to be working with is S here, and it's all the numbers between 1 and 12 except for 7, 9, and 11. And the operator we're going to look at is the divides operator, which is x divides y if x is a factor of y. So now let's figure out what the points are in this set, in this relation. So what does 1 divide? Does 1 relate to anything else in this set? Is it a factor of any other number in this set? All of them. Okay, what else do we have in here? So does 2 relate to anything else in the set? Does it relate to itself? Yes. Does it relate to 3? No. It does relate to 4, though, right? And all the other even numbers that are in this set. Now, we could do this for all the numbers, but we couldn't write down all the points, right? So I did this on a smaller set so we could write down all the points, because this is something that you have to do on your homework. Okay, 3 relates to what? Itself, because it is a factor of itself. It relates to 6, 9, except 9's not in there, and it relates to 12, right? Now, can you start to see why we use the divides relation rather than writing down all the points? It's a pain. So we have some general ones that we actually like to tell you what the operation is rather than actually telling you what the points are, but sometimes we give you binary relations where we actually tell you what all the points are. So I assume you can finish this by figuring out what 4 is a factor of and what 5 is a factor of and 6 and so on through all the points. Okay? So that is left to you guys. But there are ways that we can draw this. So there are many different ways we represent relations. So the first way is just to list out the set. So actually the first way I gave you is this, where we actually list the set that we're operating on and we tell you what the operation is. We can also list it by the points. And we can write it a different way, which we've seen before. Okay, so that's another way to write it. So it's all the points, x, y, where x is a member of S, and y is a member of S, and x divides y. So this bar means so that, and this bar means divides. And I know it's confusing. The so that goes with the parenthesis, the curly braces, so you don't use that unless you have curly braces. So this is like the form. This is stuff that's actually in the set, and these are all the conditions that have to be met for that to be true. And so R is a subset of S cross S, right? Because the set of all of the pairs there would be 1, 1, 1, 2, 1, 3, so on. But then also 2, 2, 2, 1, 2, 3. We don't have 2, 1 in this particular set. So I'm going to give you some other examples, but we're going to use some smaller ones so I can fit them on the page with my fat marker. Okay, so let's just go back to the definition right quick. So a binary relation is a set of ordered pairs. It's a subset of A cross B, where A and B are sets. And the first example you guys gave was the Cartesian plane. And we also mentioned f of x equals x squared, and another way we could write that is the set of points x comma f of x, where x is in the reals, and f of x equals x squared is also in the reals. That's a binary relation, like we just mentioned. So we have lots of different ways of representing them. Here's another example, or just a reminder that the cross product of two sets is the set of points x, y, where x comes from the first set and y comes from the second set. Sorry about that. So I just gave an example where we write out all of the points in A cross B, where I have A, the set A is equal to the set containing the elements A and B, and the big set B is equal to the set containing the elements 1 and 2. So we can write out all the points. So you can see that the first element comes from the set A and the second element comes from the set B. You can also make it in a matrix where you put all the elements of B as the columns and all the elements of A as the rows. and then you put a 1 if there's a member in that set. So if we're doing the entire cross product, that entire matrix is all 1s. If we do a subset of it, then some of it, a strict subset, then a subset of those will be 0s. Any questions? Okay, so here's an example subset that's a relation on A cross B. So if we give you a set R, which is a set of 2 points, that's an A cross B because little a comma 1 and little a comma 2 are both points in that set. It's a binary relation between elements of A and elements of B. It can be also defined by a definition, just like we've been giving before for some of them, the set of points little a comma x, where x is in B. And I didn't use a variable for A because I already knew what it was. So how would you represent that in a matrix, the set R? What goes in the rows? No one has any idea. All the members of A go in the rows. We just did that example. Am I going too slow? We had a set A cross B, and A is the set A comma B. B is the set 1 comma 2. The Cartesian coordinate or Cartesian product of those is the set of all the points where I take the first element from A and the second element from B. And here's the actual cross product of those. A comma 1, A comma 2, B comma 1, and B comma 2. That should be easy and very straightforward. Now, a standard representation for cross products is you list all the elements of the first set as rows and all the elements of the second set as columns. And then you put a 1 if you have the point A comma 1 in the set. I put a 1 here. If I have the point A comma 2 in the set, I put a 1 there. If I have the point B comma 1 in the set, I put a 1 there. And if I have the point B comma 2 in the set, I put a 1 there. Any questions on that? Okay, so then I gave you an example of a subset because this matrix is not interesting, right? This all ones matrix is not interesting at all. That's the entire cross product. So I usually don't use a matrix to represent that. I just write A cross B, right? Because then someone else can list all the elements and I can save myself some work. So then if I give you an example set, say, for example, R is a subset of A cross B. That's what this is right here. Sorry if that's a little bit unclear. So that's supposed to be the subset relation. And this should look like a sideways U, and that should look like a flat line. So R is just these 2 points. So a binary relation can be any subset of any cross product. So a lot of interesting ones have names, and they have actual like operators to go with them. Or comparisons like less than. Less than is actually a binary relation. Equals is a binary relation. Any function that I have is actually also a binary relation. Any function on the Cartesian coordinate plane. All right, so I gave another alternate definition of this, which could just be writing down the form of every point in there and specifying what's true about the points. So every point in R actually has an A as the first component in each element, and the second one is an element of B. So that's just another way to write down R. Now the matrix representation for any binary relation on the set A cross B has to make rows for all the elements of A and rows for all the elements of B. So that's what we're going to do. So we know we have A down the rows, so we have to have A and B, and we need B across the columns, so we need 1 and 2. Now, I gave you the set R, which had A, 1 in it, and A, 2. So where do I put 1s? The top row? Anything else? No, the rest get 0s. So this is a matrix representation for this relation. All right, there's one more representation that we sometimes use for binary relations, and that is called a directed graph or a digraph. So we usually put the points from the starting set on one side and the points from the other set on the other. So we have A and B here, and we have 1 and 2 here. And then for this set, we have an arrow from A to 1 because A1 is in the set. And we have an arrow from A to 2 because A2 is in the set. And we don't have any other arrows. Since this is a binary relation on A cross B, I can't actually have any arrows from B to A. We only can have arrows from A to B. Has anybody heard of a one-to-one mapping? Or one-to-many mapping? And many-to-many mappings? What kind of mapping is this? This is a one-to-many mapping. So if the binary relation was all of the pairs, like of A cross B, that would be a many-to-many mapping. So this is a mapping of the set A onto the set B, and we don't have a definition. B doesn't map onto anything in B. Little b doesn't map onto big B, but this is a one-to-many. We're not going to really work on one-to-many or one-to-one or any of that. I just wanted you to know what it is. So one-to-one, I would have an arrow between all of the points. There would be exactly the same number of points in both sets. And one-to-one, there would have to be exactly one arrow in between each pair. And one-to-many means there's more than one arrow coming out of something on the left. And many-to-many means you have lots of arrows all over the place. Okay, so you're probably wondering, why do we do all this stuff? We do all this stuff because we care about particular special kinds of binary relations, which are on sets crossed with themselves. So graphs that are in the Cartesian coordinate plane are examples of that. So that's the reals crossed with the reals. So they actually fit in this category. So any relation that's on pairs of two pairs of the same set is a special relation, and they have certain properties. So when we looked at divisibility before, when I said, okay, let's see what 1 relates to. 1 related to everything, right, including itself. And then 2 related to 2 and all the other even numbers. And then 3 related to 3 and all the other numbers divisible by 3. And 4 relates to 4. So one property of special relations is whether or not every single possible x relates to itself in the relation. And that's called reflexive, a reflexive property. So for all x in the original set S, x comma x is in the relation. So R is reflexive. This is a definition of R being reflexive. So let's do a couple of examples that might be a little bit easier to not be so abstract. I'm going to make up a new relation, and it's going to be L of xy, and x and y are going to be people, and L of xy is going to be person X lives with person Y. Now, my first question is this reflexive? Do you live with yourself? Yes. You might not be able to live with yourself, but you probably do. Okay? So if I ask the question, is L reflexive, the way you answer it is to write the definition. So for all x, L of xx. And then you decide, is this true or false? We don't do it by example. So you have to come up with some kind of argument that this works. And usually, if I'm doing a relation like this one, it's just by the definition of lives with. So how would you define lives with? Same dorm room. So two people, so X lives with Y if X's address is this and Y's address is this. That's one way to say, right? You could have lots of different definitions, right? What if everybody lived in the woods and you defined lived with as if you lived within 10 feet of someone else? You can make different definitions, right? Depending on where you were living. But most definitions would say, you know, you have the same address or you're within the same building, something like that. You have a funny example? No? Okay. All right. So by the definition of living with, everyone lives with themselves. So usually when I'm asking you about whether something's reflexive or not, I'm actually asking you sort of how universal is this relation, okay, in some way. So a justification that everyone lives with themselves cannot involve a list of all the people unless I have a finite set that I start with, right? So now if I did say everyone in this class was my set of people that I was working with, then we could make a list of all the pairs of people that lived with each other, right? So I'd have to check with every person and then see if any of their roommates were in here and put that in the set if they were. And that would be how I would construct the set. And I could prove that it was reflexive by listing all of the people and themselves and show they all live with themselves. But it doesn't make sense to do that with the lives with because I can just use the definition. So if you can, you should use the definition to figure out whether something's reflexive. So here's another property. Another property of relations is a symmetric property. And you probably, if you think about it for a second, will actually know what a symmetric property is. So let's see if we can write a definition. I'm going to say for all x and y in our original set S, if xy is in R, then what? Yx is in R. Is lives with symmetric? Yes. I'm not going to do it by example. Again, it comes from the definition. Lives with means they have the same address, so it doesn't actually matter which person you write first. Right? By the way, I'm not going to usually ask you to prove these, but you do need to be able to answer the question whether something is reflexive, symmetric. We're going to look at a few more properties. So how about transitive? So we've looked at transitive before in the context of logic, and we said the transitive property was like hypothetical syllogism with implication. So when we had A implies B and B implies C, then we get A implies C. So what symmetric says, or transitive says, if I have 3 points in S, if I have x, y in R and I have y, z in R, then I get x, z is in R. Is lives with transitive? Yes, because if John is my roommate and Bob is John's roommate, then Bob is also my roommate. Now, this relation that is reflexive, symmetric, and transitive, if we have a relation that has all three of those properties, then it is called an equivalence relation. Can anybody guess why it might be called an equivalence relation? I heard an answer. What was it? Yes, because it partitions all the people into people who live with each other and everyone else. So I could think of, if I was going to divide up all the universe of people, this lives with operation divides people into sets where everybody in the set's equivalent if they live with each other. We've talked about one equivalence relation before, and that was the mod operator. Right? So let's go back to the mod operator and see why it is an equivalence relation. So anytime somebody asks you if something is an equivalence relation, you just need to check whether it is reflexive, symmetric, and transitive. Okay, so let's be more specific about what mod is. So mod is an operator on what set? The integers crossed with the integers, right? So this relation, R, the mod relation, is going to be on the set S cross S, or I'm just going to use Z, sorry, Z crossed with Z. And the relationship is going to be, let's use a number, right? So we'll say, so the mod is going to be, mod what number do you guys want to use? Let's use 3, because we've done a lot of examples with that. So mod 3 is going to be our operator that we'll use, and what that really means is that the set's going to end up being x comma y, so that x mod 3 is symmetric to y mod 3. So this triple equals there means is equivalent to or is symmetric to. That's two different ways to read it. It doesn't matter which one you say. So what this means is x and y relate to each other if I divide each of them by 3, I have the same remainder. So you can also recognize if something's equivalent, an equivalence relation, if the definition actually goes back to the word same. Because they have equivalent something. Something's equivalent about those things. So just to give another example of an equivalence relation on people is gender. Right? So if I make a relation that's like person X has the same gender as person Y, that's an equivalence relation because all the people who are female will be matched up with all the people who are female. And that's an equivalence relation. Let's go back to mod, though. Okay, so let's actually do a smaller set just so we can see what we're talking about. Let's do okay, so let's do S cross S where S is equal to the set containing 1, 5, 8, and 9. And we're going to look at the mod 3 relation on that. So first we want to figure out what are all the points in R. So I'd like you to try to write those points on your paper. So check out 1 and do mod 3 for all of these, and then see which ones have the same remainder if you divide by 3. And if they do, then make a point with those two. The point should be of the form, like I might have 1, 1, 1, 5, 1, 8, 1, 9 in there. I should check all of those to see if they're actually in. They're only in there if 1 and the other number has the same remainder to mod 3, if I divide by 3. So other points could be like 5, 1 could potentially be in there, right? Because having the same remainder mod 3, it doesn't matter which one is actually first. But 5, 1's not in there, right? Because 5 divided by 3 has a remainder of 2, and 1 divided by 3 has a remainder of 1. So they don't have the same remainder, mod 3, so they're not actually going to be a pair. So 5, 1 will not be a pair. So let's start figuring out. How about 1, 1? Is that in there? Yes. And in fact, this is reflexive because 5 has the same remainder mod 3 with 5, right? And 8 has the same remainder mod 3 with itself. And 9 has the same remainder mod 3. Okay, does 1 have the same remainder as anything else? No, because there's nothing else that is equivalent to 1 mod 3 in the set, right? Because this 5 is equivalent to 2 mod 3, so is 8, and 9 is equivalent to what? Mod 3. What's 9 equivalent to? What's the remainder? 0 or 3 mod 3, whichever one you want to say is fine. Okay, so 1 doesn't relate to anything else, so we're kind of done with 1. Now 5 mod 3 is 2, and 8 mod 3 is 2, because 6 is divisible by 3, so I divide all that out, and what I have left is 2, so the remainder is 2. So since 5, 8 is in there, 8, 5 is in there, because all we're checking is if they have the same remainder, so it doesn't matter which order I looked at them. So 8, 5 has to be in there. Okay, we already said that 9 is 0 mod 3, so it's not relating to anything else but itself, right? And we've already figured out what 8 relates to, so we're actually done. So let's check out our properties. Reflexive is for all x, xx is in the relation. And we have that, right? Because we have 1, 1, 5, 5, 8, 8, and 9, 9. And in fact, whatever set we use for mod will always be reflexive because of the definition. If they have the same remainder, so one number always has the same remainder as itself. That is the argument, so it's reflexive because no matter what x is, that's really what for all x relates to x actually is asking me. So symmetric is asking me for all x and y, if xy is in R, then yx is in R. So that means that x mod 3 is equivalent to y mod 3 implies that y mod 3 is equivalent to x mod 3. Is that true? Yes. That's always true. Because of the definition of mod, right? And the definition of the equal sign. So, in fact, when you're checking these properties, you should write down the definitions of the property, and then you should plug in the definition for the relation into the property. So you can check to see if that predicate calculus statement is true or not. So now we need to check transitivity. So there's our definition. Is for every pair of points where xy is in R and yz is in R, then xz has to be in R. So transitivity is the most pain in the butt to check. Because I need to check all the pairs of the points. So I need to look at 1, 1. There's no other point 1 anything. So I'm not going to break this implication with this, right? So 1, 1's fine. 5, 5. Another point that matches is 5, 8. So if I have 5, 5 and 5, 8, this says that 5, 8 has to be in there. Well, duh, it is. Because that was the second point, right? So actually checking the reflexive points in transitivity is a waste of your time. Because it's always going to be true, right? So if I check XX and then XY and then see if XY is in the set, it's already in the set, okay? So you don't need to check those. So all I need to do is check these. So 5, 8's in the set. Again, I don't need to check these because if I have 5, 8 and then 8, 8, that would give me 5, 8, which is the point I started with. But I do need to check this. So I have 5, 8 and 8, 5. So I need to have what? 5, 5, and I do have it, so that's good. Now I need to check 8, 5 as the starting point, so I have 8, 5, and I have 5, 8, so I need to have 8, 8. And I do, so this is therefore transitive. So you want to check all pairs of points, but they have to meet the condition on the left in order for you to worry about the value of the implication, right? Because remember that implications are true if the hypothesis is false, right? So if I can't find 2 points in this form, I don't have to check this implication because it's going to be true. If I just find one, but not a matching point, so if I have an xy, but nothing that starts, so if I have 5, 8, and I've already checked 8, 8, and 8, 5, there's nothing else with 8 anything, so I don't have to check anymore for 5, 8. Okay, so if I write this definition out with this, the other way I can do this is to say x, by the way, you don't have to write the mod 3 twice. You can do this. Because really, actually, if I write it out twice, I can use a regular equals. If I don't, then I have to use the triple equals. Because it's like keep reading so you actually know what the equals means. So you can use a regular equals if you write mod 3 on both sides. You can use a triple one if you don't. So you can just write mod 3 once. And sometimes people put it in parentheses. And we read this, x is equivalent to y, parentheses, mod 3. We don't say the parentheses, but we kind of have a little pause, and then we say mod 3. It's like in this parallel universe where everything that has the same remainder, when you divide by 3, they're equal. Okay, so that's what this says. xy is in R says x is congruent to y mod 3, and xyz is in R means that y is congruent to z mod 3. And I'm going to check to see whether that actually implies that x is congruent to z mod 3. Now, we can prove this. So we checked all the pairs because we were on a limited set. But let's say we were actually looking at all the integers. If we were going to do it for all the integers, we actually do need to show that this works. So let's write it again and show it. So all of those are integers. So if we know that x is congruent to y and y is congruent to z, then x is congruent to z. So if x is congruent to y mod 3, they have the same remainder if I divide by 3, right? So what that really means is x is equal to 3 something plus something else, right? So it's 3 times some integer plus the remainder. And y is equal to 3 times some other integer plus the same remainder because they are congruent mod 3. So we already know that actually y is equal to 3 times some number plus this remainder. And so now we actually can say, so this Rx is the same. So now we know that z is equal to 3 times some other letter. I got to make up letters. That's by the definition of mod 3, right? So therefore, x and y now have the same remainder, right? And x and z do. So we've actually just shown that x and z have the same remainder, mod 3. Because if this is true and this is true, then all 3 of these have to be true. That's just by the definition of mod. Any questions on that? So I'm trying to head off your questions ahead of time because normally I get the question, do I have to check all the points? Yes. Do I have to write down the definitions? Yes. Do I have to prove for all? Yes. But we're not writing like really formal proofs. You just need to show that these things are actually true. Okay, so we showed that mod is an equivalence relation, and we can make the argument that it is for no matter what the divisor is that we use. It is an equivalence relation because it divides all the numbers up into equivalence classes. So, and we've been using that when we did truth tables for arithmetic proofs, right? When we talked about divisibility for like n squared minus n being divisible by 3 or something like that, then we were actually using the fact that we could divide up the numbers into categories and then deal with each category separately. That's a normal technique that we use in proofs, and this is why we can do it. It's because these are equivalence relations. We couldn't do it if there wasn't a way to do this mapping. So if they weren't reflexive, symmetric, and transitive, we couldn't actually do that. So there's a few other properties that we want to learn about. But before we do, let's actually draw our relation here. Let's draw it in a matrix. So we had 1, 5, 8, and 9 should go down the rows and across the sides. And we have the mod 3 operator. And we're going to make the matrix for our relation. And we already said it was reflexive, so 1, 1's in there, 5, 5 is in there, 8, 8 in there, 9, 9 is in there. Any reflexive relation, when you draw the matrix, will have ones on the diagonal. Okay, now we also had 5, 8 in there, and we had 8, 5. So a symmetric relation how can I define what happens with a symmetric relation in terms of what the matrix looks like? If I fold it over at the diagonal, then the ones will match up and zeros will match up. right? So these two things are across from each other, and everything else in here is zeros. Now, the sad part is that transitive doesn't have an easy way to look at the matrix and tell if it is transitive. Okay, so we have to do more work for transitive, and I'm going to tell you what that work is after we write some more definitions. Okay, so we've just defined the property of being symmetric. There's another property called anti-symmetric. That is interesting. Now, I know you probably don't think any of this is interesting, but equivalence relations are not particularly interesting, right? Like once I define it, I'm done. There's nothing really interesting about it. It doesn't tell me anything I didn't already know. I already know which things have the same remainder to mod 3. I'm just dividing them up into classes. It's useful to do, but it's not particularly interesting. We have a lot more interest like lives with. It's not interesting. Like once you know who lives with who, you're done. Okay? But there's other things that are more interesting, and anti-symmetric is one of those things. And anti-symmetric is the abstraction of less than or equal to. So that's what you should remember. In fact, it's an abstraction of less than. So not less than or equal to, just less than. So less than has this transitive property we talked about before. That's not what this has to do with. The abstraction is that for all x and y, if x relates to y, or xy is in R, then yx is not in R. So that's what that abstraction is, right? If x is less than y, then y is not less than x. So this entire section on binary relations is about abstractions of relationships like equals. That's an equivalence relation. Mods, equivalence relation, less than, anti-symmetric. And we'll also define a partially ordered set, but first we have to define anti-symmetric. So this actually doesn't look very hard of a definition. However, I've been teaching this a long time, and people's eyes cross when they see this, probably because it's just a weird word. So let's actually just try to draw a matrix of a relation that would be anti-symmetric. Does it matter what I put on the diagonal? Does this care about diagonal? Well, what's on the diagonal? It's XX, right? So if I put something on the diagonal, I put XX is in R. That's definitely true if I put something on the diagonal. And if it's there, it implies that XX is not in R. So actually, I made a mistake. This is asymmetric. That's probably why everybody's eyes cross. This is asymmetric. I didn't write the full definition of anti-symmetric. So actually, if we do asymmetric, that means there's no symmetry whatsoever for ones. Okay? So asymmetric means that we don't actually have any symmetry at all, except we're allowed to have zeros across from each other. So if I put a 1 in here at AB, what do I have to have at BA? I have to have a 0. It has to be the opposite. I'm allowed to have zeros across from each other, so it's okay to put AC is 0 and put CA is 0. If I put a 1 at CB, I have to have a 0 at BC. So if I had to make up an asymmetric relation, anywhere I put a 1, I just have to make sure that there's a 0 across from it. And I can't have any 1s on the diagonal at all, because that breaks this implication, because XX is in R, would imply that XX was not in R, and that's broken. Okay, so anti-symmetric is really the same, except it doesn't care about the diagonal. So you're allowed to have ones on the diagonal with anti-symmetric. So how do we write it? We write it as for all x and y, if x and y is in R, and yx is in R, then x equals y. So it looks complicated, but basically all it means is it's asymmetric, except you can have any ones you want on the diagonal or not. It doesn't matter. So it doesn't actually care about the diagonal. But otherwise, if I have xy in the set, I cannot have yx in the set. So let me ask you a question. Is lives with asymmetric? No, it's symmetric. And there's very few things that can be both symmetric and asymmetric. The empty relation is both symmetric and asymmetric. So the empty relation is the set of no points. The empty set has a lot of properties. Okay? So it's not a trick question. It's just that is the only number. It's like, just like 0 in the regular number. 0 has some special things. So does the empty set. But otherwise, you can't be both symmetric and asymmetric at the same time. Okay, how about anti-symmetric? Is lives with anti-symmetric? No. Not unless nobody lives with anybody but themselves. So that's not the empty relation, right? But if everybody had a separate domicile, then lives with would be anti-symmetric. Because the only people anybody lived with would be themselves. So there are situations where we can have these and have symmetry and anti-symmetry at the same time. But it only involves when we have lots of zeros. But if you have any ones, we can't have them at the same time. If there's any ones at all outside the diagonals, symmetric and anti-symmetric can't happen at the same time. Okay, so now let's try to make an anti-symmetric matrix. Now, it's real easy to make one. You can just put zeros everywhere. But let's make one that's not actually just all zeros. Let's put a couple of ones in there. I'm going to put one at AC, and one at AA, and BB, and BC. So now everywhere that I have a 1 off the diagonal, I have to have a 0 across. So at AB, it doesn't matter. So at BA, I can put a 1 if I want to. And so if we separate this into the diagonal and off diagonal, on the diagonal we don't care what's there, and off the diagonal, if I have zeros, if I have ones, they have to be across from zeros. And in this case, I actually made everything strictly anti-symmetric across, so we don't have any 0-0 pairs. So in this case, we have, so another way to write this set would be A, comma A. So I just said A and wrote B. Sorry about that. A, comma C. B, comma A, B, comma B, and B, comma C. So this set is anti-symmetric, and I can check that by saying, okay, I have AC. Do I have CA? No. All right, so this one's all right. BA, do I have AB? No, so that one's okay. BC, do I have CB? No, so this one's okay. And I only need to check the ones off the diagonal for anti-symmetric. Now, I like to use a little analogy. So when we're looking at some of these relations, we're going to use the matrices to figure out a pattern. Yes, Philip. Yes, that first point is AA, because we have a 1 in the AA position in the matrix. Okay, now, when we're looking at matrices, we need to be able to tell what properties do they have. Reflexive, symmetric, transitive, anti-symmetric, and asymmetric. And the last one we'll do is irreflexive, which means all zeros on the diagonal. And I'll write that down in a second. But I want to give you an analogy. So, how many people have ever had a peanut butter and jelly sandwich? Has anybody not had one? Does anybody not know what a peanut butter and jelly sandwich is? Okay, I'm just checking. We might have some people from, I don't know, some place that doesn't have peanut butter and jelly. Okay? So, how do we make a peanut butter jelly sandwich? We have 2 pieces of bread, right? And we have some jelly and we have some peanut butter. And you usually put jelly on one side and peanut butter on the other. Right? But you could also do things like put jelly on both pieces and not make peanut butter and jelly, just make jelly and jelly. Right? Or you put peanut butter on both sides and get your mouth stuck together. And why am I talking about this? Okay, so what we're going to do is we're going to pretend that our matrix is a table where we're making peanut butter and jelly sandwiches. Okay? And I'm going to lay out all my bread where I have positions in the matrix. And I'm going to put jelly on all the ones that have zeros. And I'm going to put peanut butter on all the ones that have ones. Because eating a jelly sandwich is not a problem. But eating a peanut butter sandwich can be a problem for some people. Now, maybe you have extra saliva or something. But it's kind of hard to eat a sandwich with excessive amounts of peanut butter, right? Okay, so maybe we're going to make our sandwiches and we have a cool sandwich making table. Yes? Well, it's fine. We'll do some 2x2s and things like that. So the question is, what happens if we don't have an odd size matrix? It's okay. There's still a diagonal, and there's still even number of stuff on the other sides. Okay? So we have a table, and we're going to, this table has a hinge right here, and it's going to so quickly mash those things together you don't have to pair up all the bread. Okay? So I'm just going to fold my table over, and it's going to make all my sandwiches for me. If I'm anti-symmetric, I don't get any peanut butter whole sandwiches. However, I could get some half peanut butter sandwiches on the diagonal. But that's okay, because I could stand that much. But a whole sandwich I can't do. So anti-symmetric is a 3.5-year-old kid that won't eat a whole peanut butter sandwich. But he will eat jelly, a whole one, a whole peanut butter and jelly, or a half of anything. So that's how we can remember this, is that we don't want any whole peanut butter sandwiches. So don't match any ones with ones across the diagonal. Now, how does the peanut butter jelly analogy help us with asymmetric? What kind of sandwiches am I allowed to have? Jelly, peanut butter and jelly, half of jelly. Anything else? No, because we're not allowed to have half of peanut butter, or whole peanut butter. Okay? So that's how it can help us. Now, how about something that is reflexive? So reflexive has all ones on the diagonal. So what property do I have with my peanut butter jelly sandwiches if I'm reflexive? All of my half sandwiches are what? Peanut butter. So if it's reflexive, all the half sandwiches are peanut butter. If it's irreflexive, that means none of the diagonal elements have any peanut butter. No ones on the diagonal. So all the half sandwiches are jelly. And transitive, I don't have a peanut butter jelly analogy. Sorry. Okay, so the last thing we need to do today is talk about how do we compose relations, because that's actually going to help us figure out when a relation is transitive or not. So you've done this many times, but you might not realize it. So when we compose two relations, it looks a lot like transitivity, And the reason is that I can actually, when I do a relation, it's almost like a mapping in between two sets, and a composition is like a sequence of two mappings in between two sets. So A cross B is a mapping from A to B, some subset there, some kind of mapping between A and B, and then B cross C is some mapping from between sets B and C. And composition tells me how to go from A to B and then B to C. So I like to think of it like flights. So we can have relations that consist of all the pairs of cities that an airline goes to. So like when you go on the airplane, you get a magazine and you flip to the back, right? And it has all these little arrows when there's flights between cities, right? You guys seen those maps with the arrows between cities where the airlines fly? Okay, well they have those. And when you look at that, you can see why sometimes you have to take two flights somewhere, right? Because there's no direct flight from where you're going to the place. But the airline will say, we fly between Raleigh and Paris. Even if they don't, they actually fly from Raleigh to New York and go from New York to Paris, right? So they're using composition all the time to figure out what flights they actually can do. So if you go to a search engine and you put RDU and Paris, it's going to look not only for Raleigh to Paris direct, it's also going to look for Raleigh to somewhere, and that same somewhere to Paris, right? So it's actually looking for a composition of the two binary relations where the binary relations is, where does this airline fly? And is it possible, have you ever gotten a flight that was with two different airlines? Yes, because then it will look for, after it looks for all the pairs within airlines, it will look across the airline. So it will look at one relation of cities to cities from one airline and then cities to cities from another airline and see if those middle cities overlap. So it's a way to get me from A to C, telling me how I have relations that go from A to B and B to C. And then now, if I compose them, I can now have a new relation that's A cross C that came out of the old ones. So let's say that this first one is going to be American Airlines, and this one's going to be US Air, okay? And we're just going to put a couple of cities. US Air loves Charlotte, so we're going to have Charlotte in there. So we'll say RDU and Charlotte will be an A. Actually, I'm going to make that B. And let's say we just want to go to Europe. And we're going to try to figure out which ways we can go. So there's my three sets. So now I need to define which flights go where. So let's say we have American has the pairs RDU and let's get rid of this one. Let's put we have RDU to DCA, and on US Air we're going to have RDU to Charlotte, and to DCA. DCA is the Reagan National. Okay, so what are all the possible flights where I take American? So this is A cross B. And let's do, I'm sorry, that's a confusing example. Sorry, I had it straight in my head. Let me try again. Let's make it a little bit easier. All right, so let's make the definition. So R1 composed with R2 is going to be the set of A comma C, where AB is in R1 and BC is in R2. So like I said, I take one flight from R1 and then one flight from R2, and that tells me all the places I can get with a 2-flight jump, the first flight being from R1, the second flight being from R2. Now, if I need to compose two relations, what needs to be on the rows here? Looking at this. So the columns in R1 have to match the what? The rows in R2. So this has to be Charlotte and DCA. So one way of writing this is with an X with a circle in it. When you write the relations with with letters, you put a little circle, and if you write it with matrices, you usually use this one. Let's do this. Okay, so now we're going to make two different matrices. So this means I can go from RDU to Charlotte and Charlotte to Munich, meaning I can go from so my final result is going to be RDU and DCA, and we'll have Paris and Munich as the columns. So if I go from RDU to Charlotte and Charlotte to Munich, then that's going to give me an RDU Munich point, right? Okay, so I'll go RDU to Charlotte. There's no other Charlotte routes, so I'm done with that point. I don't go to DCA from RDU, so that's fine. I don't go to Charlotte from there. I do go from DCA to DCA, and I can go from DCA to Paris. So I can take two silly flights from DCA to Paris. That's what happens when I make up an example on the fly. Sorry about that. Okay, so now we actually know these are, out of these two relations, these are the ways I can take a pair of flights where I start at either RDU or DCA and I end up in Paris or Munich. So that's what composition does. Now this is the same as matrix multiplication. How many people have done a matrix multiplication before? How many people have not done a matrix multiplication before? Please raise your hand if you haven't, because I will talk about it if you haven't. Okay, how many people have done it in binary before? Does anybody have an idea of what doing it in binary would make a difference, how that would make a difference? So let's just do a general one. So it actually is slightly different in binary, because every time we do a times, we're doing an and every time we do a plus, we're going to do an or. Okay, so I'm going to multiply these two, and I'm going to teach you a little trick for doing binary matrix multiplication. So the trick is I'm going to take each row, because what I'm actually going to do, if I want to see if I can go from 1 to D, first thing I'm going to check to see if I can go from 1 to A, and then A to D. In this case, the answer is yes, but I'm also going to check, does 1 go to B, and does B go to D? Yes, it does. But 1 doesn't go to B, so I don't worry about that. And then 1 goes to C, and does C go to D or not? But we get a 1 in there because I OR all three of those together. So 1D in my resulting matrix is going to be 1A and AD, or 1B and BD, or 1C and CD. So the new element is actually going to be the or of all of those things. That's not a matrix thing. That's just an or. So or of everything. All right, so is this one true? 1A and AD, is that true? Yes, because I do have a 1 at 1A and I do have a 1 at AD. So that's a 1, so I don't even care about the rest of that. That's going to be 1, right? Because an or will give me a 1 no matter what. If you do regular addition, it will tell you how many options there are. So that is totally fine. So you can do regular matrix multiply and get the numbers you would normally get, except that if I get something bigger than 1, just cap it down to 1. So my trick is I treat this like a magic wand, and the magic wand is has a magnet on it where there's 1s and doesn't have a magnet on it where there's a 0. Then I turn it, and I slide it across the other matrix. So I'm going to slide a 0, 1, 0 across here, and I'm going to pick up 1s here, and I'm going to pick up 1s there to give me my new row. So I'm going to pick up 1, 1, 0 with this 1 right here, because when I turn it and slide it across, it's going to pick up that first row. And this one's going to pick up the bottom row, and I'm going to OR those two together to get my new top row. So it's going to be 1, 1, 0. And I'll tell you this again, so don't worry if you're not getting it, but I'll tell you the second one. The second one picks up the first row and the second row, and then ORs them together to get the second row of my new matrix. So I'll get 1, 1, 1 in this matrix composition. And in the last one, this one picks up the last row, so my composed matrix of these two, so this is R1 and this is R2, is going to give me 1, 1, 0, 1, 1, 1, 0, 1, 0, where we have 1, 2, 3 on the left and D, E, F on the right. So we'll do some more on composition next time, and we'll also define transitive in terms of composition.